Welcome back to the lecture on Hopfield networks and Boltzman machine, part 2. What we now want to leave Hopfield networks as such and look at some related approaches. So, Boltzman machines are also recurrent neural networks that can be seen as the stochastic generative counterparts of Hopfield networks. The non-determinism allows the system to come out of local minima. So I would say that is the main feature here. Boltzman machines were invented in 1985 by Jeffrey Hinton and Terry Savnovsky. So they are also called stochastic Hopfield networks with hidden units. So as you remember, all units in Hopfield network were mutual input-output nodes. So one could say Hopfield nodes is a one-layer neural network, while the Boltzmann machines may have hidden units. But as for Hopfield networks, we have symmetric connections between units. Finding optimal states involves relaxation. So, and now we talk about optimal, I don't talk about necessarily local optima, as many of the hill climbing or steepest descent approaches that we looked at during the course. Here we talk about a method that has some probability of getting out of this local optima to find the global one. So in the Boltzmann machine setup, we have introduced some kind of relaxation procedure where the student can, so to say, potentially jump out of local minima. And this technique is called annealing, simulated annealing. So Boltzmann machine are after the Boltzmann distribution in statistical mechanics, which is used in their sampling function. They also get energy-based models. So actually, the state changes can either occur deterministically if the delta energy value is less than 0, or stochastically with a certain probability. And that probability normally is defined as 1 divided by 1 plus e raised to minus delta energy divided by a parameter t. And t is the so-called temperature of the model. And one important idea in annealing, we'll come to that, is that you start with a high temperature and decrease the temperature during the process, which of course then would affect the probability for making state moves. Looking at the process in a Boltzmann machine, on this slide there is a simple scheme. So actually we look at one example at a time, and for every example we run the network in like 2 phases. So the positive phase is defined by you in a way clamp or lock the visible units with the pattern specified in the example, and then let the network settle using this annealing technique, and then you record the outputs of units. And you can iterate that a number of times, and then you do it again, but then you let all the units free, and you follow the same procedure. You do annealing, you reiterate, etc., and then you compare the outcome of the two different phases, and then one compute the odds that both units, that 2 units in each pair of unit is coactive and the negative phase. So this gives us a set of probabilities, and actually then what we do when we update the weights, we base it on some statistics. So we update them with respect to the differences between the probabilities calculated from the two phases. K is just a learning rate. You have seen it many times now. It's just a damping factor. So this is the procedure. We will next go and talk a little about the simulated annealing process. So the source of inspiration for simulated annealing is actually annealing as it happens in metals, which means that you initially heat the solid state metal to a very high temperature, which makes it possible for the atoms to move around relatively freely. But then you slowly cool the metal down according to some schedule. So if you start very high and cool it down very slowly, then you can achieve that the atoms will place themselves in a pattern that corresponds to the global energy minimum of a perfect crystal. So of course you can see the analogy here. What we want is a optimized solution to our problem, depending on how we model our problem. That means that we want to find a global minimum. So that's the analogy we strive for. So one way of describing simulated annealing, the steps in such an algorithm would be the following. So first you initialize. You start with a random initial configuration. You initialize a very high temperature value of that parameter. And then you propose a change, a move, or a change of the configuration. And then you calculate some score. In our case, it's the delta energy. If we still keep to that property of the Hopfield network that we inherit, so we calculate that delta due to the proposed move, and then depending on the delta. The move is accepted or not according to the earlier given formula. And of course, as you can understand, depending on now which step in the iteration we have, in each step we have a certain temperature. In the beginning we have a high temperature, which gives a higher probability for making changes. But when we then, for the next step, we update the temperature, and we do it by lowering it in a certain pace. And of course, when we lower the temperature for each iteration, the likelihood that actually a move will be taken diminish. So we continue then this until we came to what could be called a freezing point. And of course, a freezing point needs to be defined for each domain where we apply this in. This slide just shows you the phenomena that in contrast to a greedy algorithm, the possibility to still take moves, even if you reach the local minimum, you can still take these tentative moves that may bring you out of the minimum, and hopefully then in the end towards a global minimum weight. You can see in the end at the bottom. One issue with Hopfield networks and restrictive Boltzmann machine in practice is the connectivity, the unlimited connectivity of this network. So therefore, there are a number of approaches where one, in a way, different ways limits the connectivity. So one such architecture is called restricted Boltzmann machine, RBM, and where you decide that the neurons as a system must form a bipartite graph. So this a bipartite graph is a graph where there cannot be any connections between the neurons or nodes within one of these parts. So the graph is divided into parts, and there is a group of neurons in each, and between neurons in one group there cannot be any connection. So it can only be a connection between neurons that are in two groups. And actually, the two groups are typically the visible the visible neurons and or units or the hidden units. This method is rather old, but actually it got more popular just 10 years ago when the researchers, together with Hinton, developed some better algorithms for this method, and after that is come into more wide use. Another related approach is called bidirectional associative memory, abbreviated BAM. And the interesting difference here is while Hopfield networks are auto-associative, which means, if you remember, that in auto-associative memory, you can, in principle, only retrieve objects or patterns that are more or less of exactly the same form. So you enter a partial description, and you can get the full, but of the same format-wise, the same kind of object. While in hetero-associative memory, and BAM is an instance of that, you can actually retrieve totally different patterns. And the reason for that is possible in BAM is that BAM work with actually two separate layers, and in one layer you can have items on one format, and then in the other layer you can have items with a totally different format. But the two layers are fully connected, so this means that there is an unlimited way of really connecting the two classes of patterns. So by having these layers where there are free format in both, you could possibly live up to the demands of what is termed hetero-associative memory. We don't have much time to go into the details of BAM, but on this slide you can find a simple example that illustrates somehow how things work. So actually what you do is you store association between various patterns in this memory, and you can also observe up to the left that the two patterns that we associate can have totally different form. So actually what is possible to do is to create a matrix from the sum of the outer products of these associated vectors, and then that matrix can be used. So when you want to retrieve a pattern, you can then, in this case the B, the second part, you can multiply by the vector and get the other part back. And if you do want to do the opposite, you can use the transpose of this matrix. So there are no details here, sorry for that, but it's just to give you a feeling for how this retrieval can be done, and also the fact that you in this case can have dissociation between totally different structures. Another interesting variant of associative memory is what's called the coherent network or self-organizing maps, SOM. So SOM implements a form of unsupervised learning, and in a way takes potentially complex nonlinear statistical relationships between high-dimensional data and maps it onto a low-dimensional display. So actually, one of the results here is to do dimensionality reduction, as it is thereby compresses information while preserving the most important topological and metrical relationships of the primary data on the display. It may also be thought of to view some kind of abstractions. It was invented in the 1980s by Tuve Kononen in Finland. The map is predefined, and usually it's a finite two-dimensional region where nodes are arranged in a regular grid, and you get the idea from the right. And then you can see you have input vectors below, and then one can say that this model is fully connected in the sense that all inputs are actually connected, not to each among themselves, but all the inputs are connected to all the elements in this two-dimensional grid. So actually, the SOM network, in the SOM network, if one look at the nodes in this flat space of nodes, apart from being connected to every input, it's also that node keeps a weight vector where one weight for each connection, so that is built up during the training phase. But in the testing phase, actually what the system does is it for each test case tries to find the node where with the weight vector that gives the smallest magical distance to the test case. So by this we have finished this lecture on Hopfield networks and related work. Thank you very much for your attention. The next lecture, 6.8, will be on the topic of convolutional networks.